In this video, we're going to do an example titration calculation problem, and we're specifically going to do it in the buffer zone. If you recall from class or from the map of titration calculations, the buffer zone is where you've partially converted your weak acid or base to its conjugate species, and this is the definition of a buffer solution, appreciable amounts of a conjugate acid-base pair present. That means that if we're anywhere within this buffer zone, we can use the Henderson-Hasselbalch equation to calculate the pH inside the Erlenmeyer flask at any given time. Let's try it. If 25 milliliters of 0.0125 molar hypochlorous acid, HClO, is titrated with 10 milliliters of 0.0200 molar sodium hydroxide, what is the final pH? The pKa of HClO is 7.54. Well, we're going to quickly calculate the equivalence point and the midpoint to see if we're at either of those. The equivalence point is based off of the moles of acid equaling the moles of base that have been added. So the volume of base to do that will equal the molarity of the acid times the volume of the acid divided by the molarity of the base. In our case, the volume of base we've added at the equivalence point will be 15.6 milliliters. Well, we haven't added that much. We've only added 10. Let's see if we're at the midpoint. The volume at the midpoint is half that of the equivalence point, or 7.8 milliliters of sodium hydroxide. We have not added that, we've added more than that, so we're somewhere between the midpoint and the equivalence point. We want to check for the midpoint because here the pH would equal the pKa of the acid in question. Since we are between the starting point, where we haven't added any sodium hydroxide, and the equivalence point, but we're not at the midpoint, we need to use the Henderson-Hasselbalch equation, and that encompasses just 4 steps. First, we're going to calculate the moles of hydroxide and HClO using the information given in the problem. We're then going to use that hydroxide to calculate how much ClO minus, the conjugate base, has been generated. Then we calculate the remaining moles of HClO, and then plug everything into the Henderson-Hasselbalch equation and crunch the numbers. Let's do it. The relevant equation for us, chemical reaction equation, is HClO plus OH minus becomes irreversibly ClO minus, the conjugate base of HClO, plus H2O. So this sodium hydroxide we're adding is going to react with the HClO to make ClO minus. We have added 2.00 times 10 to the minus 4th moles of hydroxide with this volume and concentration of solution. And initially, in this 25 milliliters of the HClO, we have 3.12 times 10 to the minus 4th moles of HClO. From our chemical equation, we know that for every mole of OH minus we add, we're going to get a mole of ClO hypochlorite ion generated. So the moles of hydroxide directly becomes moles of ClO minus, 2.00 times 10 to the minus 4th moles of ClO minus now present. This moles of ClO minus was generated from the initial moles of our HClO acid, so we have to subtract the moles of ClO minus from our initial moles of HClO to figure out how much we have left. That'll be the 3.12 times 10 to the minus 4th minus 2.00 times 10 to the minus 4th. So we now have left, after the reaction with hydroxide, 1.12 times 10 to the minus 4th moles of HClO. These two values for the ClO minus and the HClO are what we're going to plug into the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation states that pH equals pKa plus log of the ratio of the base over the acid. And we can do this in moles or molarity, it doesn't matter. That's going to be 7.54 plus the logarithm of 2.00 times 10 to the minus 4th divided by 1.12 times 10 to the minus 4th. Crunch that down, you get a final answer of 7.79 for the pH currently in the flask. This pH makes sense because we have more of the conjugate base present than the conjugate acid, meaning we would expect the pH to be higher than the pKa of the acid. I hope this step-by-step example helped. I'm always available in my office hours, and good luck studying.